we are going to spend this next video investigating numeration systems, particularly those ancient ones that I mentioned in the previous video. So this starts with some definitions, and it's very simple. How do you define a number? Think about that for a second. What is a number? Often people think of numbers as things like this or that. Those aren't actually numbers. A number is more like an idea or an abstraction. So it's an idea or abstraction that represents a quantity. Okay, that's what a number is. And again, a number is a quantity of things. Animals have been shown to have a sense of number, that a quantity, their one quantity is larger than a number or than another quantity. That's obviously some sort of evolutionary benefit, right? More food means survival, and so humans, we can often look at a grouping of symbols compared to another one and tell how that there's more in one than the other. And so that's the idea of number, just an idea of quantity of something. Earlier, I wrote numbers like 327. So that's actually called numerals. Those things are numerals. Numerals are symbols for numbers. Okay, so 7 is a numeral, right? 7 is a numeral because it represents the quantity, that many things, okay? Numerals were at the very earliest stages of this idea that we should represent quantities with things. Often numerals were probably developed before number words were. In fact, at many years ago, there was not a need to represent many things, right? You were counting that I had, this much land or this many sheep or something. And so often the words that represented numerals were either one, you had one sheep, or many sheep. There was no 2 or 3 or 4. It was either you had one thing or you had many things, okay? But there were some numerical representations, and those often started from the idea of tallying. And tallying is basically saying that if you have one thing, you can represent it with maybe just one line. Or if you have 2 things, you can represent them with 2 lines. Or if you have 3 things, you can represent them on a cave wall, right, with 3 lines. So that's the system of tallying. Several thousand years ago, about by 3400 BCE, the Egyptians had created kind of the first system of numeration for numbers up to and exceeding 1 million. And these groups of tallies are how their system started. But later, we had to start grouping. We had to start to have this idea of grouping because we couldn't just keep using this system forever and ever, right? If we needed to represent 79 things, right, we wouldn't want to, just make 79 little marks. We had to have a way to group stuff together. And one of the easiest ways for early civilizations to group stuff was by hands, using hands, right? Because you've got them built into your body, and you've got convenient counting device, 5 fingers, right? And so often, if you would group things by 5, that was even called a hand. And today, certain parts of the world even still use that. They count by hands, right? One hand has a value of 5. 2 hands has a value of 10. And so think about how you might even represent that with the idea of hands if you had to say, well, let's do this. If you had this many dots, which just represent some things you're counting, right? How would you represent that with the idea of hands? Well, if we put them in groups of 5, this would represent 1 hand worth of things. This would represent another hand worth of things. So we could say that this collection of items could be stated as 2 hands and 2. So you've got this remainder over here. So you've got 1 hand, 2 hands, and then 2 more. So try to do this one on your own. I'm going to just draw out a grouping of dots arranged and using this idea of hands. And this, and we'll go here. So go ahead and pause, take a look at that and see if you can represent that using the idea of hands. So you might have seen, noticed, again, we've got some groupings of 5 here, 5 here, 5 here, another group of 5. So that's 1, 2, 3, 4 hands. And then we have 1, 2, 3 left over. So we could say that is 4 hands and 3. Now, using that system, you were still sort of limited, right? The most you could really represent is the number 24 things, right? Because you got 4, like on your body, right? You think about body 5 things, right? So we've got hands is the base 5, right? The most you can do is 5 things. Okay, 5, 5, 5, 5. And once you get to, if I did another one, 5 hands and 4, or 4 hands and 4, if you added another dot here, this would make 5 hands, and they didn't actually have an idea for 5 groupings of 5, right? What do you call that, right? And here's where you can start to connect that to the previous video's activity with those base 5 groupings, okay? So start to kind of linking these ideas. So if you're using the idea of hands, the number 24 is sort of the max that you can go up to. 4 hands and 4 more. All right. And that leads us to the idea of just the idea of having number bases in general, okay? So number bases. So a base is the number of object used in the grouping process, right? So the base is the number of objects used in the grouping process, right? In the previous example with hands, hands is base 5. Because we were grouping 5 fingers together, right? 5 units together to make one group of 5. Okay, so that's the idea of having a base. We're going to extend that to different ideas coming up. And so the first one, ancient numeration system we're going to look at is the Egyptians. So the Egyptian numeration system. And they use pictures, symbols called hieroglyphics. Maybe you've heard of that before. And so they used a base 10 system, okay? So base 10. But not quite like we do. And so here are the pictures that they used to represent different numbers. So I'm going to start over here on the right. You'll see a stick, right? A stick had a value of 1. A heel bone had a value of 10. a coiled rope was a value of 100. This lotus flower, 1,000, a pointing finger, 10,000, tadpole, 100,000, and the astonished man, 1 million. So every time they go from one symbol to the next, they're increasing by 10, okay? And so a base 10 system has groups of 10. And so what I want you to try to do, well, I'll do the first one, is think about the number 2,342. And actually you pause the video and see if you can think about how you might represent the number 2,342 using all of these symbols. So pause and go ahead and do that. So what maybe you did was you looked at these symbols and you said, all right, well, I see that the 2,000 can be represented with 2 of these lotus flowers. So there'd be 2 of these, which would make 1,000. We've got 300. So that would be 3 of these coiled ropes. We have 4 40s, right? 4 is 40s. So that's 4 of these heel bones. And then 2 is going to be 2 of these sticks. So if you drew this out using the Egyptian numeration system, it would look like this. Again, 2 of the lotus flowers, 3 of the coiled ropes, 4 of the heel bones, and 2 sticks, right? That's how the Egyptians would represent the number 2,342. So can you think of any drawbacks to this system? One drawback is that it can get pretty long, right? If you're trying to represent a really big number, you could be using lots of these symbols, and these could get drawn out super, super long. Another thing, and I didn't tell you this to start intentionally, I didn't tell you which way to draw these. And the Egyptians actually sometimes wrote them from left to right, but they also could have written this completely backwards. They could have put it like this. And the lotus flower is a hard one, right? It's actually not bad. Right? This is the same symbols, just in a completely opposite order. This still represents the number 2,342, because sometimes they wrote them left to right, sometimes they wrote them right to left. It wasn't really consistent. But what this is an example of is what we call an additive numeration system. Additive numeration system. So the Egyptians used this type of system, which is basically where we're adding the symbols together, right? And each symbol, right, is a power of the base that's repeated as many times as possible. Remember how I talked about when we were doing base 5? We used those powers. Again, 10 is 10 to the first, 100 is 10 to the second, 1,000 is 10 to the third, 10,000 is 10 to the fourth, 10 times 10 times 10 times 10. Here we've got 10 to the fifth, 10 to the sixth, and then again, this is 10 to the 0. And so these additive numeration systems use this idea. In fact, I'm going to give you a nice definition here. An additive numeration system uses some number, we're going to call it B, that's our base, B for base, and symbols that represent the number 1, B, which would be 10, B squared, which is 100, B to the third, which is 1,000, etc., like I showed a moment ago, for the powers of the base. Numbers are written by just repeating these powers of the base for the necessary number of times, right? So we just wrote 4 of these heel bones to represent 4 tens. So we just wrote the symbol 4 times, okay? And then, again, in an additive system, it doesn't matter the order that you put them in. but you then just add up all those numbers at the end. There's another system, ancient system, the Roman system. You may have seen, this is probably the most common other numbering system, Roman numeration. Romans also used base 10. They also used base 10, but they had a modified additive system because in addition to the normal powers of the base 10, 10, 100, 1,000, they also gave symbols for 5, 50, and 500. And so there are 7 common symbols that you'll see in the Roman numeral system, and they look like this. 1 is an I, 5 is a V, 10 is an X, 50 is an L, 100 is C, 500 is D, 1,000 is M. And you may even recognize C and M are pretty common. If you ever work within metric systems, C is centum, which means 100. Big century has 100 years. Centipede has 100 legs. M is for mille, right? Mille is 1,000. Mille means 1,000. Millennium is 1,000 years. And millipede, theoretically has 1,000 legs. So now let's try to take a look at some Roman numeral. Can we write a number using this Roman numbering system? So let's use the same number we did before. 2, 3, 4, 2. Now, before we do this, there's a more sort of recent way that Roman numerals have been used, but it's not what the ancient way was. So we're just going to use the additive system, additive numeration system using these symbols. So 2, 3, 4, 2 would look something like this. We would have 2 of the thousands, so that would be M, M. We have 3 of the hundreds, which are here, so that would be C, C, C. We have 4 of the tens, so that would be X, 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 X. And we have 2 of the ones, which is I, I. So this would be how we would represent the number 2,342 using the Roman numeration system. Go ahead and try that on your own for the number 1,996. Do it the same way that I just did it. Go ahead and pause and try that. Hopefully, if you tried that, what you came up with was a single M. I'll put these up here. A single M for 1,000. You had a D for 500. You had 4 C's for 4 more hundred. So 500 plus 400 is the 900 here. Then we go to 90, so we got L for 50. And then we have to make 40 more, so that's going to be 4 more. So we had 1 L, 4 X's, 1, 2, 3, 4. And then we had 6, so that's going to be 1 V and 1 I. So that's what 1,996 might look like using the Roman system. Okay, it's very similar to the Egyptian, just some different symbols, and they gave those 5s. Now, there's a newer version of the Roman system. It's been around for a long time. It was recognized by the Romans, but it hasn't really gained popularity until about the last 200 years. So there's a way to condense both of these using what they call the subtractive principle. Okay, the subtractive principle. One thing you might notice about the way that I did these earlier was we took them, we wrote them from left to right. So larger values were on the left. Larger values on the left. Remember I said for the Egyptians, it didn't really matter the order. The Romans said, hey, order matters a little bit. We're going to start with those largest values on the left, working to the right. And by doing that, it actually gave way to this subtractive principle. So what that means is when you use the subtractive principle, If you take a smaller value, like an I, and place it to the left of a larger value, like V, then you actually end up subtracting it. I'll give you a really simple example. So let's just talk about the number 4. Let's talk about the number 4 in Roman numerals. If you used only the additive principle, it would be I, right? 4 I's. But if you use the subtractive principle, you can say, I want to take 1 away from the 5, and I would place it to the left and write it as IB. And again, that's saying I placed a smaller value to the right of a larger value, which means I'm going to subtract it. If we wrote VI, it goes in order from larger values on the left, smaller on the right. So this would be 5 plus 1, which is 6. This would be the value of 6. This would be the value of 4, because we're taking 5 and we're subtracting 1 from it. Now, you never will see subtracting more than just 1, right? Typically, the way it's done is once you reach 3 consecutive symbols of one symbol, that's the most you can use. If you would need a 4th, then we don't use the 4th and we use the subtractive principle instead. That's the common use of Roman numerals. So let's go ahead and try 1,996 again. So we use that up here, and here was the full-on additive approach. And let me show you all the Roman numerals again. So see if you can try the number 1,996, but now use the subtractive principle. See if you can find the condensed way to write it. I'll let you take a moment to do that. Go ahead and pause. And so let's think through this. So for the 1,000, we would still need the M. So when we get to 900, in the previous version, what we did was we wrote a D followed by 4 C's. We're not going to do that here. What we're going to do instead is say, can we, because 900 is really close to 1,000. So can we take 100 away from 1,000? And yes, we can. So we're going to take 100 subtracted from 1,000 and write it like this, CM. So this portion here, the CM, represents the 900 differently than we had done up top. So that CM is representing that 9 right there, all right? So the first M is for the 1,000. The CM is for the 9. Okay, and just to sort of note that, so we can keep track, this M, that's going to be the 1,000. This is going to be the 9 for the 900. And now we've got to represent the number 90. Now think about how we did that in the previous problem. We had an L followed by 4 X's, 50 and 40. Instead of adding 50 plus 40, we're now going to take 100 minus 10. So the way we would represent that is, here's our 100 and here's our 10. We put the smaller one in front, XC. This is going to represent that 9. So again, the M is 1,000, the CM is the 900, XC is the 90, and then to represent the number 6, we don't want to subtract here. We will do just like we did right here and write VI. So this is, I'll even note that, there's our number 6. MCMXCVI is the same as this big thing up here, okay? But notice how it's condensed, right? It's a little smaller. So these two sections here and here used that subtractive principle. And one of the things you might notice, right? Still, this is a little tedious, right? You got to really pay attention to, am I adding, am I subtracting, am I writing out this really long number? So just to do a little practice here, why don't you take a moment and try, again, writing We'll just do one for practice. Let's do this number. 2,146. So 2,146. And use that subtractive principle if you need to. So take a moment to try and do that. And what I will do, so you can see it on the screen, I will recopy and repaste the Roman numerals chart. So 2,146. Ready, set, go. So let's see what this is going to look like. So we start with the 2,000. That is going to be MM, 2,000. For 100, we can just use a single C. For 40, we're going to use the subtractive principle. We're going to take 10 away from 50. So we will write that as XL. And then for 6, again, we're going to use the additive principle. 5 plus 1 will go a V and then an I. So this is how we would represent the number 2,146 using Roman numerals. Reshare. There we go. So now they start to get a little fun. You thought those were fun. Now we're going to get real fun. So the next one is the Babylonian system. The Babylonian numeration. So the Babylonians used base 60. Not base 5, not base 10. They used base 60. And you can imagine some of the challenges to that. But what's interesting is that elements of base 60 have sort of even continued throughout history. Think about how we measure time, right? We measure time as broken up into 60 seconds, 60 minutes. And so there are things from that Babylonian system that have carried through. And so how do we represent Babylonian numbers? We used only actually 2 different symbols. So the basic symbols starting from 1 and going up to 59 used a combination of something that sort of looks like a T, like that, and something that looks like sort of like a boomerang almost, something that kind of looks like that. Okay. So this is the number 1 and this is the number 10. Okay. And so let's talk about what this is going to look like. Just for example, if you wanted to represent, say, the number, I'll just paste them all right here. So here are 4 examples. So in the Babylonian system, if you wanted to represent the number 23, you would put 2 of those little boomerangs for 10 and 3 of these little T's for 3. If you wanted to represent the number 6, well, then you've got 6 of those little T's. The number 40 would be 4 of those little boomerangs. And then the biggest number that you can represent sort of in the first grouping is 59. 5 of the boomerangs and 9 of the little T's. All right. So that right there represents the number 59. So you're wondering, I know, well, what do we do if we go more than 59? We'll get there. We'll get there, I promise. So the Babylonians were actually the first civilization to really investigate numbers and develop the concept of place value, which you've certainly heard of, right? So the Babylonians introduced the idea of place value. And place value is a power of the base. And again, the Babylonians used base 60. So place value involves 1, 60, 60 squared, 60 to the second power, 60 to the third power, etc. Kind of like the other systems used, but the key is when you start to use a place value system, the basic values or the basic symbols, sorry, the basic symbols, all these things up here, they had different values depending on their location, right? Depending on their location, right? Where is the symbol within the, in relationship to other symbols? That's going to sort of tell you what the actual value is. And so, if you saw, let me just again do a little copy and pasting so we can investigate this. So this is how the Babylonians would have represented the number, the value 135. So can you figure out where that came from? You kind of have to imagine like two separate columns. Here's the first column, and here's the second column. The first column over here, in fact, let me start over here on the right. So over here on the right, this is what I showed you earlier, right? Each of these is sort of in that ones place, okay? In that ones place. And as before, this represented 10, and then these represented the 5. So you can see 10 plus 5, 15. So that's representative in that first column there. But over here, look what happened. This is now a different value. There's 2 of those 10s, right? But they're in the tens place, right? And so this is really saying it's 2 times 60. It's not the tens place. That's kind of how we would think about it in our system, but it's really they're in the 60s place. Okay. So they're saying you've got 2, right? 1, 2. It's those symbols for ones. 1, 2 times 60. 2 times 60 is 120 plus 15. Here is where we get that 135 from. So let's take a look at another example, a bigger number to help you really internalize this, because this can be a little bit tricky. In fact, something that I think can help when we make sense of this is first even sort of writing out what the different place values look like. And so the Babylonian system, kind of like the way we do our system, you put the larger place values on the left, and the smaller place values on the right. Okay, so larger place values on the left, smaller on the right. And so the first, we'll call it a column. Again, those are going to be worth ones. The second column will be worth 60s. The third column, if we have to, that'll be worth 60 squared. Now, what is 60 to the second power? That's actually worth 3,600. So anything in this column, we're really counting how many 3,600s do we have. If we have to go another one, then it's 60 cubed, right? For this example, we won't have to do that. So I'm going to really group these by columns for this next one, okay? And so we're going to make a really big number here, all right? We're going to make a really big number, and I'm actually going to sketch out the symbols, and we're going to see if we can figure out what this would look like. Okay, so we have, I know I'm bad at this, the little boomerang symbol. We've got a second boomerang symbol, and we've got two of the T's, right? So we got that for there. Here, we're going to have 3 of the T's. And they're not just a T, they kind of have like a little triangle at the top. And then over here, we're going to make 3 of these boomerangs. So we're going to see if we can figure out what the value of this number would be. So it's easier to kind of work right to left, I think, when you're trying to make sense of these initially. So over here, these are the symbols for 10, right? So because they're in the ones column, the symbols themselves have a value of 30, and we're multiplying them by whatever place value we're in, which is ones, okay? So this has a value of 30. Once we move to the second column, we first look at the value of the symbols themselves. 3 of those T's has a value of 3, but we're going to multiply it by the place value. So this is representative of 3 groups of 60, and that is equal to 180. And then we're going to look at this third column over here on the left. So this has a value of 10, 20, 21, 22. So the symbols themselves represent 22. But then we multiply it by the value of the place value, which is 3,600, right? 60 squared, okay? And that is that's a pretty big number, right? And so what is the value of this entire thing? Well, I'm actually going to grab my calculator and do that 22 times 3,600. So that first column has a value of 79,200. 79,200. And then if we add all 3 of those values together, this plus this, we get a total of 79,410. That would be the value of this group of symbols, okay? So again, what you're doing is you're examining the symbols to figure out their value, 30, 3, and 22. And then you're multiplying that by the place value. So now let's work one backwards. So let's say you have the number 7,950. And what you want to do is represent it using the Babylonian system of numbers, like draw the picture, okay? So how do we do this? I want you to pause the video and see if you can play around and figure out what this would look like, okay? I'm going to keep going. I'm going to use the column approach. The Babylonians did not use columns like this, but I think it's helpful when you're first learning it. So this is going to be our ones column. This is our 60s column, and this is going to be our 60 squared or 3,600 column. Now, if you think back to the very first exercise we did, remember in the previous video when we used those yellow base 5 tiles and we wanted to use the smallest number of tiles possible, and so we would use the biggest grouping possible. That idea is the same here. So we want to pack as much as we can into this first column, okay? So our first question is, how many 3,600s fit into 7,950? So how many of these can fit into here? That's really the question, right? And so the way you might do that, if you were going to use a calculator to help you, you might take 7,950 and divide it by 3,600, right? Divide it by 3,600. And what you get is this decimal, 2.2 something, something, something. So what that tells us is that 3,600 fits in 2 times, okay? So we think about, well, then how do we write the number 2? We write the number 2 with 2 of those t's. Okay, so 2 of those t's has a value of 2 times 3,600, which is equal to 7,200. So those 2 symbols, because of where they are in the number, have a value of 7,200. Well, how much do we have left then? If we subtract the 7,200, what we're left with is 750. So now, again, notice that we're smaller than 3,600, so we're shifting over into here, into this column. So now we got to figure out how many groups of 60 can fit into 750. So we go back to the calculator, and we divide 750 by 60. And it's 12.5. So we're going to use the 12. So we have to figure out how to make 12 groups of 60. Well, one of those boomerangs is 10 plus 2 of the t's makes 12. 10 plus 1 plus 2, there's our 12. 12 times 60 is 720. So if we subtract 720, that tells us we have 30 more to go. Notice 30 is less than 60. So we're going to cram those 30 over here into the ones column. How do we make 30? From 3 of our boomerangs. And that is our 30. 30 groups of 1 is equal to 30. So this group of symbols is how we would represent the number 7,950. But I do want to point something out that I'm going to come back to later. The Babylonians, when they wrote it, it would sort of look like this. There we go. So again, we've got our 2 t's here. We've got our boomerang 2 t's here. And we've got our 3 boomerangs there. So I'm just going to throw it out there without even answering my question. Do you notice anything that might cause a bit of a problem here? Or be a little bit confusing? I'm going to keep going. So just go ahead and pause. I'm going to have you try one of these to start on your own. Can you represent the number 2,473? See if you can draw that number using the Babylonian system. So what this is going to look like when you're all done, I'm just going to go right down to pasting what that grouping would look like. It would look like this. So again, why is that? Well, if we know we don't need something over here in the 3rd column because it's less than 3,600. So we're starting in the 60s column. So how many 60s can fit into this number? 41. 41 60s can fit into 2,473. And we represent 41 for boomerangs and 1 t. If we subtract that, 41 times 60, we get 2,460, leaving us with 13. And then we got to put that in the next column, which we represent with a boomerang and 3 t's. This is what the number 2,473 would look like. So one of the problems with the Babylonian system is, and maybe you thought about this from before, is that sometimes it's hard to tell like where one column starts and one begins, right? Where's the next grouping start and where does the next one begin? That can be a little bit tricky. And then there's one other problem too, which I haven't mentioned yet. And we're going to do one last one. Imagine we had to try and represent this number. This is going to be our last one we do. 10,800 21. And if you want the practice of pausing and trying to write this out using Babylonian, go ahead. I'm going to keep going. I'm going to use the column method here because I think that it helps illustrate things and really prove the point here. So again, we got the ones, we got the 60s, we got the 60 squareds, which again is 3,600. So I'm going to go through this one a little bit quicker here. What we end up with is 3 T's here. 3 T's is the number 3. 3 times 3,600, if we multiply that out, would be, let's see, that's going to be 10,800. 3 times 3,600 is 10,800. So once we get that, then we subtract and we see we only have 21 to go. Well, 21 is smaller than 60, so we're not going to put anything here. We're just going to jump to this last column, and that's going to be represented with a boomerang for 20 and a T for 1. So there's our 21 times 1. There's our 21, and we've represented a number. But the way the Babylonians would actually write this would look like this. And so I'm going to ask you if you can see the problem with the Babylonian system, the major problem. There's nothing in this 60s column, right? So how do you know, right, if I didn't show you any of this stuff down here, and I just showed you the pictures, how might you interpret it? If I saw that, what I would think is that these numbers represented 21, they belong here. But if I saw that, I would think that those 3 T's actually belonged in that column. And that would be 3 times 60, not 3 times 3,600. I would think that this number actually is 180 plus 21, which is 201, not its actual value, 10,821. So what's the problem? The Babylonians had no concept yet of the idea of 0. We use the number 0 if we want to show that there's no value to that place, right? We're shifting these over to this column. That's what we do in our numeration system, but the Babylonians didn't. And so that caused a major problem, a major issue. In fact, the number 0 has an entire history of why it was not acknowledged as a value, as a number for thousands of years. There's a whole book, one of my favorite books, is called The Number 0 by Charles Seif. And it, at least the first 80% of the book is about the history of it. And it's fascinating. But it wasn't really allowed to be used until later. Now, the last major new system that we're going to talk about here is the Mayan numeration system. So the Mayans. Again, the Babylonians helped us by introducing place values, but they still lacked a 0. So Mayan numeration. And what I'm going to do is I'm going to show you their symbols here. And just take a look. Mayans used base. Can you figure out what base they used by the way it looks? Mayans used base 20. They used a base 20 system. But what other thing do you notice here? The Mayans did have a value of 0. Yay, good job, Mayans, right? They introduced that idea, right? And they also used the ideas of place values, okay? And so this is how they would write the numbers from 0 up to 19. Now, they didn't write things from, like the other ones that we've seen, we typically write our numbers from left to right, with the larger values on the left. The Mayans did it a little bit differently. They stacked their values, right? So they had their smaller place values on the bottom, and they had their larger place values on top, larger place values. So instead of going from left to right, they went from top to bottom when they're looking at their largest place values. So that's a little bit different, something we'll have to adapt to a little bit as we investigate this. Now, there's one other little quirk to the Mayan numeration system, and it had to do with the way they created their calendar. The Mayan calendar had 18 months of 20 days, and then they had 5 holidays to make 365. But because they had 18 months of 20, they used their numbering system in kind of alignment with their calendar. And so here's how what their place values looked like. Their smallest place value was the ones place, just like we've seen before. Their next place value was 20, because it's base 20. But the next one up was 18 times 20. Not, you would expect it to be 20 squared, 20 to the second power, but it's not. It's 18 times 20, and it has to do with, again, their calendar system. And so the value of 18 times 20 is 3,600. So as we start to build these, we're going to keep that number in mind. As you go up further, now the next place value would be 18 times 20 to the second power, which has an actual value of 7,200. If we go another larger place value, it's 18 times 20 to the third, which has an actual value of 14,400, right? And we would keep going up larger and larger place values. So one's on the bottom, then 20s, and then 18 times 20, which is the value of 3,600. And then we keep squaring the 20. We keep adding a power to every 20 as we go up past that, right? So that's a little bit trickier. So it's not a true base 20 because of that 18 there. So let's look at what some of these might look like. Okay. So the first one that we will do is the number. We're going to look at the number 326. So I'm going to do the number 326. And let's look at how we would represent that. And so I'm going to have to show, what I'm going to do here is take our symbols. And it's a pretty easier one to recognize. The symbols actually make a lot of sense, but I still want to be able to visualize these as we go through this. Okay, so we're going to work from, again, the bigger values at the top, the smaller on the bottom. So earlier I had mentioned at the bottom we have ones. Next up we have groups of 20. The next group was, remember, 18 times 20, which was 360. And then above that was 7,200. So if we start with the number 326, it's less than 7,200. It's also less than 360. So what we're going to be doing is we're going to see how many 20s can fit into 326. And if you divide 326 by 20, what you'll see is that you can fit 16 groups of 20. All right, so we're going to have 16 groups of 20 that fit into 326. And so we're going to find the visual for 16, which is this one right here. So we would write 3 stacks with a dot, 5, 10, 15, 16. So that would go on top to represent 16 groups of 20. That's 320. And then we subtract and we have 6 left over. And then beneath this, we would put the image for 6, which is one line with a dot. So this is the number 6. This is the number 320. And so you see how they stack bottom to top, smaller place values, larger place values. So for this next one, I'm going to draw the picture and see if you can figure out what the number would be. So the picture is going to look like this. So we have that on top. And then we have that beneath. And then we have that beneath that. So go ahead and pause the video and see if you can figure out what the value of this symbol would be using the Mayan system, okay? So if you pause the video and tried that, let's see how you did. So again, we have to keep these place values in mind. So first of all, the picture itself, I'm going to focus on the picture itself. This is the number 16, 5, 10, 15, 16. So this is 16, and it's in the ones place. So that is a value of 16. This is 5, 10, 11, 12, and it's in the 20s place value. So that has a value of 240. And then this has a value of 5, 6, 7. And what's the value of its place? 360, right? Remember, it's 18 times 20. So 7 times 360 is equal to, if we grab a calculator, I didn't have that number written down. 7 times 360 is 2,520. 2,520. So again, because of the places, notice the larger values on top. When we add all those together, you end up with a sum of 2,776. This would be the value of these symbols. So let's try one more. One more of these for you to try on your own. So I think what I'll do is I'll give you the number. We won't go too crazy here. Let's go with the number 106. So the number 106. Let me grab the symbols for you to still see while we're working on this. So see if you can use this chart and then represent the number 106. All right. So if you pause the video, the number 106. So where do we start? We start thinking about our place values. We have ones, we have 20s, and then above that, 360s. 106 is less than 360, so we're not going to have any of those. We're going to say, how many 20s do we have? So we think division. How many 20s fit into 106? 5 of them. So 5 times 20 is 100, right? So how are we going to represent the number 5? With this thing right there. So we're going to start with a single bar on top. So there's the number 100. What do we have left? We have 6 left. So there's our symbol for 6. So for 6 times 1, to make that 6, we're going to stick that right underneath. And this is what it would look like. Again, here's the number 6, and here's the number 100 on top of that. So the number 106 is a fairly simple representation of that Mayan system. So again, I know these are going to challenge your brain, challenge your thinking, but that's really, really good. It's really important for you to go through that. Try some other numbers, right? Try to go back and look through some of those and try some other numbers, because what this is really making you do is think about the idea of place values. And it's going to give you such a good, strong foundation for what you're going to have to understand about our place value system, our base 10 system moving forward.